Ionization energy and electron affinity. The energy required to remove the most loosely bound electron from a neutral gaseous atom is called the ionization energy. If you consider the metal as M, then to remove the first electron, it will require ionization energy 1 to form the M+. Then, if we want to remove the second electron from the M+, it will form M2+. This is called IE2, that means ionization energy, second ionization energy. Then again we can form M3+ from M2+ by removing one electron from the outer shell. These are called the successive ionization energy. Ionization energy 1, ionization energy 2, ionization energy 3 are called the first ionization energy, second ionization energy and third ionization energy respectively. Suppose group 1 metals are lithium, sodium, potassium, rubidium, cesium, francium. All these elements have their valence shell 1 s electron. Suppose for lithium 1s2 2s1. For sodium the valence electron is 3s1. So to remove this first electron, that means s electron from the valence shell, this is called the first ionization energy. Ionization energy depends on the following factors. Number 1, the size of the atoms. Number 2, the charge on the nucleus. Number 3, how effectively the inner electrons cells screen the nuclear charge. Number 4, the type of electron infall. We know that from left to right in a periodic table, the size decreases in a period, and in a group the size increases from the top to bottom. So when the size increases, the ionization energy decreases. Again, it depends upon the charge on the nucleus. As the charge on the nucleus increases, the attractive force between the nuclear charge and the valence electron increases. As a result, the ionization energy also increases. If the nuclear charge is screened by the inner electrons, then the attractive force between the nuclear charge and the valence electron decreases. As a result, the ionization energy also decreases. The ionization energy also depends on the type of electron which is removed. An s electron penetrates nearer to the nucleus and is therefore more tightly held than a p electron. For similar reasons, a p electron is more tightly held than a d electron, and a d electron is more tightly held than a f electron. Comparison of first ionization energy with second ionization energy of group 1 metals. Let us take the example of lithium. It has electronic configuration 1s2 2s1. To form Li to Li plus, we have to remove one electron. This is called the energy required for this is called the ionization energy 1 or first ionization energy. Then it will acquire the 1s2 configuration. To remove the another electron from Li plus to Li2 plus, we have to disturb the stable electronic configuration 1s2 to form 1s1. So the first ionization energy for group 1 metals is IE1 is less than IE2 because second ionization energy will be more due to the removal of electron from the stable state or the field electronic state. If we see the comparison of ionization energy 1, first ionization energy of group 1 elements or group 2 elements or metals, And we see that for the group 2 metals, the ionization energy 1 or first ionization energy is double than the ionization energy 1 for the group 1 elements. We know that beryllium, the first element of, suppose this is beryllium, this is group 2, this is group 1, suppose lithium, the nuclear charge increases. This is the atomic number 3, atomic number 4. The nuclear charge increases in case of beryllium. Next, as the nuclear charge increases, size decreases. As a result, the first ionization energy for the group 2 metals is double than the first ionization energy for the group 1 metals. As you know that Na, after removing the first electron, it will from Na plus. This is the first ionization energy. If we take the group 2 metal Mg, after removing the first electron, applying the first ionization energy, we will get the Mg plus. We can see that Na plus has smaller size than Na, or Mg plus has smaller size than Mg. The second ionization energy, IE2, is more than IE1 because after removing the first electron, the second electron is tightly held. So the IE2 for the both this Na plus or Mg plus ion is more than the IE1. The removal of third electron is more harder due to the following reason. Number 1, the effective nuclear charge increases. Number 2, remaining electrons are more tightly held, which are in a complete shell. That means to remove the third electron, we have to apply much amount of energy because the effective nuclear charge increases and the remaining electrons are more tightly held in a complete cell. So it is more difficult to remove the third electron for the group 2 metals. Suppose boron 5, 1s2, 2s2, 2p1. The last electron is in the p orbital. If you consider the beryllium 4, 1s2, 2s2, the last electron is in the s orbital. So ionization energy for group 13 elements is less than the group 2 elements because we know that the ionization energy depends upon the type of orbital where the last electron exists. In case of of boron, which is group 13 elements, the last electrons is in the p orbital. In case of beryllium, the last electron which we have to remove is in the s orbital. So the p electron is easy to remove than the s electron. As a result, we can say that the ionization energy for group 13 elements is less than the ionization energy for the group 2 elements. Let us see the comparison of ionization energy in kilojoule per mole for some of the elements. The elements of period 2 are lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And the elements of period 3 are sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. If we see the value of ionization energy, we see that lithium have 520 kilojoule per mole, beryllium have 899, which is more than the lithium atom, because here we have to remove the electron for a filled cell, that means 2s2 cell. And in case of boron, we see that it has 10801 kilojoule per mole, which is less than the 899 for beryllium, because here the valence electron is in the p orbital. Again, in case of carbon, it has more value, ionization energy value than the other, because here the size is decreases from left to right. Again, in case of nitrogen, the value is 1403. Here the ionization energy more than the carbon due to the half filled cell. That means for nitrogen 7, we see that 1s2, 2s2, 2p, x, 2py, 2pz. All these have 1 electron. This is the filled, that means half filled cell, which is more stable. Due to this reason, nitrogen have more ionization energy. In case of oxygen, it has 1410. That means due to the smaller size than the nitrogen, it has 1410 value. In case of fluorine, it has 1681. That is, fluorine is the most electronegative atom. In case of neon, which have filled neon, that means 10, 1s2, 2s2, 2p6. That means stable electronic configuration, due to which we have the highest IP value in the group period 2. Again, in the next period, third period, we see the value of magnesium is more than the sodium, value of aluminium is less than the magnesium, due to the p electron in the valence shell. Again, value for phosphorus is more than the silicon, due to the half-filled stable electronic configuration for the phosphorus. Again, sulfur have less value than the phosphorus, because phosphorus have more stable electronic configuration than the sulfur. Again, chlorine have higher value than the sulfur due to the more electronegative nature than the sulfur. Again, argon is the noble gas which have the stable electronic configuration like neon, 8 electron in their valence shell, so it has the highest electronic configuration in the group in this period. The value for ionization energy in group 13 is not regular, because from boron to aluminium the value decreases as the size increases. We know that the ionization energy value decreases with increase in the size of the elements in a group. As a result, the value for ionization energy in aluminium is less than the value for ionization energy in case of boron. But the value of ionization energy for gallium, indium, thallium is irregular. The ionization energy value for gallium is somewhat more than the aluminium because the gallium is preceded by the 10 elements of the first transition series in which the 3D orbital is progressively filled. As a result, the value of gallium is not lower than the aluminium. In case of indium and thallium, these two elements are also after the 10 elements of the transition series. So the value of indium and thallium are also not lower than the aluminium. The ionization energies for the transition elements is not regular. In case of third row elements, that means hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold, mercury, the value of ionization energy is somewhat less because before the hafnium we see the 57 up to 71, lanthanum up to lutetium are the F block elements. That means these are lanthanide elements. So for the third row transition elements, the value of ionization energy is not regular. That means these have the lower ionization energy value. If we see the ionization energy value for group 13 elements, which are boron, aluminium, gallium, indium, thallium, we see that it has first ionization energy value is 0.01 kilojoule per mole, second ionization energy value 2427, third ionization energy value 3657, aluminium at 577, 1816, 2724. That means the third ionization energy more than the second ionization energy, which is more than the first ionization energy. In case of the other elements, we see that the third ionization energy value is greater than the second ionization energy value, which are greater than the first ionization energy value. Electron affinity is the energy release when an extra electron is added to form a negative ion. That means, suppose if this is lithium, when we add an electron, it will form an negative ion. The energy released is called electron affinity. Electron affinity depends upon the following factors. Number 1, size of the atoms and the effective nuclear charge. In case of hydrogen, when we add one electron to form H minus, it will release minus 72 kilojoule per mole. That means it has electronic configuration 1s1. After forming H minus, it will acquire 1s2 electronic configuration. The energy will be released in this case. Suppose in case of helium, it has electronic configuration 1s2. After forming helium minus, it will become 1s2, 2s1. That means we have to add energy. That means energy is absorbed in case of helium when we form the Hc minus helium negative ion from the helium because it has 1s2 stable electronic configuration. The different electron affinity value for elements in kilojoule per mole are: for lithium we see to form lithium negative ion, the energy release is minus 57. In case of beryllium, it has 1s2, 2s2, S2 electronic configuration. So to form beryllium negative ion, the energy is absorbed. This is 66 plus 66 kilojoule per mole. In case of oxygen, to form the negative ion O minus, it has minus 142 kilojoule per mole electron affinity value. To form the dinegative ion O2 minus, energy is absorbed, which is 702 kilojoule per mole. Again, in case of sulfur, we see that to form the S minus from S, that means sulfur, the energy is evolved, which is minus 200 kilojoule per mole. But to form S2 minus from sulfur, energy is absorbed, which is 332 kilojoule per mole. Although these have the positive energy, that means the energy absorbed in many compounds, we get the oxygen and sulfur is in O2 minus state. It follows that the energy required to form the ions must come from some other process, such as the lattice energy, where the ions are packed together in a regular way to form a crystalline solid, or from solvation energy in solution.